A beam is a properly supported structural member capable of withstanding loads that are applied in a direction perpendicular to its central axis. In this session, we are going to discuss the type and nature of the forces internal to a beam. Consider a cantilever beam subjected to a concentrated load at its free end. Suppose we conceptually cut the beam at its midpoint and choose to examine its right segment. Since the conditions of equilibrium must be satisfied for the segment, then we can write, the sum of the forces in the x direction must be 0. The sum of the forces in the y direction must be 0. And the sum of the moments about, say, point C must be 0. Since there are no loads applied in the x direction, the first equation is automatically satisfied. But how do we satisfy the second and third equations? We have a downward force of P applied to the right end of the segment. Therefore, there must be an upward force at point C equal in magnitude to P in order for the sum of the forces in the y direction to vanish. This upward force, labeled V on the diagram, is called the shear force. It is one of the internal forces in the beam. To satisfy the third equilibrium equation, it is important to recognize that P creates a moment about point C. For the sum of the bending moments to be 0, a bending moment must be present at C. The magnitude of this moment must be equal to the magnitude of the moment that P creates about C. The two moments, however, must act in the opposite directions in order for their sum to be 0. Let's denote the bending moment at point C as m. Here are the two equilibrium equations in terms of V and m. Solving for the two internal forces, we get V equals P and m equals negative P times L over 2. Here we can conclude that when a beam is subjected to a transversal load, a load that is perpendicular to the beam's central axis, then two types of internal forces develop in the beam, a shear force and a bending moment. Generally speaking, these forces do not remain constant in the beam. Their values may need to be determined at critical locations throughout the beam. In order to calculate the shear force and bending moment at a point in a beam, it is necessary to conceptually cut the beam at that point and draw the free body diagram for each beam segment. Here, it is important to recognize that any time we cut a beam, we need to show the beam's internal forces at the cut point. So, if we cut this beam at its midpoint, point C, we end up with two beam segments, the left segment and the right segment. The internal forces at the left segment of the beam at C are shown like this. For the right segment, these forces are drawn like this. At C, the shear force in the left segment has the same magnitude as the shear force in the right segment. We are using the same variable, V, to denote the magnitude of both force vectors. However, the two forces have opposing directions. One is drawn upward, the other is drawn downward. This is necessary as the algebraic sum of the two forces must be 0. The same is true for the bending moment at C. The moment for the left segment is drawn in the counterclockwise direction, whereas for the right segment, it is drawn in the clockwise direction. Since both moments have the same magnitude, their algebraic sum, therefore, is 0. Now, let's see how we can calculate shear and moment at a point in a beam. The procedure is rather straightforward. 1. Calculate the beam's support reactions. 2. Conceptually cut the beam at the point of interest. 3. Show the internal forces at the cut point and draw each segment's free body diagram. 4. Formulate the equilibrium equations for either the left or the right segment of the beam. 5. Solve the equations for the unknown shear force and bending moment. Let's illustrate this process using an example. Suppose we have a simply supported beam subjected to two concentrated loads. We wish to determine shear and moment at points C and D. Let's start by calculating the support reactions. Here is the beam's free body diagram. Here are the equilibrium equations. From the last equation, we can calculate By. By equals 3.5 kilonewtons. From the second equation, we get Ay equals 2.5 kilonewtons, and the first equation gives us Ax equals 0. Here are the results shown graphically. Now, to determine the shear and moment at point C, we conceptually cut the beam at C and draw the free body diagram for either the left segment or the right segment, whichever is more convenient. Let's pick the left segment. Here is its free body diagram. Note that I did not draw the internal axial force at C, since I already know there is no axial force present in the beam. How do I know that? Because there are no applied forces in the x direction. The relevant equilibrium equations, therefore, are from the first equation, we get Vc equals 2.5 kilonewtons. From the second equation, we get Mc equals 10 kilonewton meters. Here are the results shown graphically on the beam. To determine shear and moment at point D, let's redraw the beam. Now, cut the beam at point D and draw the free body diagram for either the left or the right segment. Let's pick the right segment this time. Here is our free body diagram. Again, since there is no axial force present on the beam, I am going to omit drawing the internal axial force at point D. Then, the relevant equilibrium equations are from the first equation, we get Vd equals negative 1.5 kilonewtons. From the second equation, we get Md equals 17 kilonewton meters. Here are the results shown graphically on the beam. Let's consider a more interesting problem. Suppose we have a cantilever beam subjected to a uniformly distributed load. Here we wish to come up with a couple of algebraic equations for calculating shear and moment at any point in the beam. That is, I want to write an equation in the form of v of x, where x is the position of an arbitrary point in the beam. When I substitute a value for x in the equation, it gives me the value of shear at that point. I also want to write a similar equation for bending moment, which can then be used to calculate internal moment at a desired point. In other words, I'm interested in representing shear and moment algebraically. To do this, let's find the support reactions. Here is the free body diagram for the beam. Here are the equilibrium equations. Solving them for the unknowns, we get Ax equals 0, Ay equals 5,000 newtons, and M equals negative 25,000 newton meters. Now, let's cut the beam at an arbitrary point, say point P. Draw the free body diagram for the left segment of the beam. Since we do not know the length of the segment, I'm going to label it as x. That is, the distance from the left end of the beam to point P is x. Now, write the equilibrium equations in terms of x. We have the sum of the forces in the y direction must be 0. That is, 5,000 minus 500x minus v equals 0. Here, 500x is the area of the distributed load applied to the segment. The rectangular load has a height of 500 and a base of x. Therefore, its area is 500 times x. The sum of the moments about point A must be 0. Therefore, v times x minus m plus 500x times x over 2 minus 25,000 equals 0. Just like the first equation, here 500 times x is the area of the rectangle representing the distributed load. X over 2 is the distance from the center of the area to point A. Hence, the product gives the moment of the distributed load about point A. Solving these equations for V and M in terms of x, we get V equals 5,000 minus 500x. M equals 5,000x minus 250x squared minus 25,000. So, these are our shear and moment equations. We can use them to calculate shear and moment at any point along the length of the beam. For example, what is shear and moment at the left end of the beam where x equals 0? V of 0 equals 5,000 minus 0, or 5,000 newtons. M of 0 equals 0 minus 0 minus 25,000, or negative 25,000 newton meters. Notice that these are the support reactions. The equations correctly give us the support reactions for shear and moment when x equals 0. What is the shear and moment at the midpoint of the beam where x equals 5? V of 5 equals 5,000 minus 500 times 5, or 25,000 newtons. M of 5 equals 5,000 times 5 minus 250 times 5 times 5 minus 25,000, or negative 6,250 newton meters. Let's do one more point. What is shear and moment at the free end of the beam where x equals 10? V of 10 equals 5,000 minus 500 times 10, or 0. M of 10 equals 5,000 times 10 minus 250 times 10 times 10 minus 25,000, or 0. The equations correctly indicate that the shear and moment at the free end of the beam do vanish. For design purposes, it is generally useful to graph these equations. We'll discuss the graphical representation of shear and moment in beams in the next lecture.